I will share my screen right now as well. So what were we doing? What were we doing last? We were talking about systems of equations. Historically, we've been going over the last week or so, week and a half, depending on how you look at the timing, about equations. More specifically, when you're graphing, when you're working with an inequality, a single equation, sometimes it's algebra, sometimes it's graphing, sometimes it's a little bit of both. And what happens is that this entire time, you've had been working with a single equation. And just last Monday, right, we were actually a combination of last Monday and a little bit before. We've been introducing systems of equations. In other words, more than one equation simultaneously. So let me write that down really quick for you. What we're attempting today is, again, finishing systems of equations. In other words, what kind of solutions occur when you have two graphs that are whizzing across the coordinate plane. And we did graphing. I know it was a little extensive, yet you all saw graphing in one shape, form, or another. And you find out that this is actually the easiest visually, but the slowest method. We also wrapped up substitution. This one was algebra heavy. But shorter, right? So that's what we've done. Today, we're going to wrap up with elimination. That's the classic name of it. Yet more modern teachers and more modern techniques have called it addition as well. I know I've mentioned that before. And then if we have time, which we should do or have graphing inequalities. And it's the same exact thing you've been graphing with a single inequality, but this time with two. So that's the whole dotted line, solid line, shading. And we might have enough time, for example, one or two. We're actually going to get a little bit further from my first section, section 305, the one that meets prior to you guys. So this will be the full-fledged, and then I'll post the video, and then those students will be able to see respectively what's going on there as well. So that's that. Okay. So what do we do now? If you look in our textbook, remember the old textbooks from Blackboard, right? I'm going to scroll up just a touch. They discuss that on page 602, that is not 602, 602, right? There is a definition. I put it in quotation marks because it's not a real crazy, hard to find definition. It's just there, a way to express it, but I'm going to tell you how to do it right now. On how to solve systems using elimination. But I'm going to walk you through it anyway, so it's not a big deal. Elimination method. So if you really need to, you can copy the definition there. But when I go through this example, you're going to see. So I'm going to scroll up now. Just a little bit more. Here's example one. So suppose they gave you a set, right? They normally give it to you in this curly brace form. 3x plus y equals 5. And then they give you 2x minus y equals 0. So it looks exactly like what we've been doing, except the layout is a little bit different, just a touch. So what is the layout that you need for elimination? I'm going to write it here on the right side. Layout for elimination is that you'll have one equation and you want all the variables on the left side, equal sign, and then a single number. And then you do that same exact thing for the second equation, or what you'll hear me say, the second row, because it's almost like they're stacked in rows, right? Row 1, row 2, kind of like that. You don't have to keep that, but so that's the layout for elimination. So that means if you ever see, if you ever see the variables not aligned as you see in example 1 right here, you have to move them. And the great thing as well is that it doesn't require any additional knowledge, right? You all know how to move variables to the left, to the right, and all that fun stuff, okay? So where do you go from there? So the first thing you have to do is this is why it's called elimination, you have to cancel out a variable. Well, if you're looking at the variables right now, you have your choices of x's and your choices of y's. And if you're to combine both of these equations together in this way, where you draw a big line right here, and you call it a big addition sign, just like this, right? That's how they combine. So the reason for elimination is that you cancel a variable out completely. The reason students or some teachers call it addition method is that you have the two equations and you're adding them together. So again, it's just whatever your personal preference is. You're looking at these two variables, what would probably be the easiest variable to cancel, the x's or the y's, based on example 1, just from observing this? What would be someone's guess?
The two y's?
The two y's, right? How come? Don't worry, I'll answer that. Thank you for answering, though. Yeah, it's the y's. Well, why? Or how come? This y has no numbers in front of it, and it is a positive version. Actually, let me put a circle around it. That'll be easier. The y on the bottom is not only a y with no numbers in front or coefficients, and it's a negative version. So they just cancel. That's all, right? So what happens here is that you get the addition of the x's. So you get 5x. These cancel out, and you get plus 0. You don't have to write the plus 0, but I'm doing it for everyone. And then you get these added together, and you get 5. And then, of course, if you divide both sides by 5, you find out that x is equal to 1, which is correct. Now, this is only half the answer. How do I get my answer to y? What do I have to do here?
You have to plug everything back. You have to plug it in.
Right. So when you hear plug it in, that sounds a little vague, right? Don't worry, I'll help everyone. I would say all you have to do is, I'm going to use pink here. You take this x equals 1, and you could plug it into either equation, the first one or the second one, because they're both the originals. I'm going to plug it into this first one right here. And you solve for y. And most of the time you can do it right where you see it. You can just put in number 1 there and put parentheses. But some students, they need to see the actual dictation of it. So I'm going to draw a little arrow down here. I'm going to rewrite 3 times 1 because they came from that x equals 1 plus y equals 5. And then as you can see right there, if you subtract 3 on both sides, you get y equals 2. positive 2. So remember, this is your answer, though be familiar if they give it to you in a coordinate form. So or x equals 1. Nope, that's wrong. X equals 1, comma 2. So either those versions are correct, but they convey the same answer. All right. So again, this is the easiest, quote unquote, of the elimination method because you can cancel out variables immediately right from the get-go. There's no extra work involved. You see it, you do it, that's it. Wait, I'm sorry. You see it, you do it, and that is it. That's it. Yeah, sorry. All right. What questions here before I go over? Now we're going to go over not numerous yet various examples so that you can see, oh, what is this that's going on?
Can you please give me the definition of what the second answer would be? What is that called?
Oh, I'm sorry. It's called this is called a coordinate point. Coordinate point or form. And that's supposed to represent when you look on the regular XY chart. I'm sorry, the XY graph. It's just that when you see this, right, they call it a lot of things. They call it rectangular coordinates. They call it the coordinate plane. They call it XY plane. There's just so many names for it. Yet without a doubt, when you say coordinate, you know you're going to graph that point. So that's what that's called. Did I answer your question?
Yes, thank you.
You're very welcome. All right. What other questions? Sorry, that was my neck. It's hurting a little bit. What other questions on this first example? All right, let's go on to number 2. So number 2, you're going to see, it's not terribly different, but well, you know, you'll see what I'm talking about. Here's example 2. And then they give you, and remember, this is all called elimination/addition method. X plus 4y equals 2, and 2x plus 5y equals negative 2. What they want to convey here is that, yes, you still have to eliminate a variable, but between x and y, what would probably be the quote-unquote easier variable to eliminate? And as you're looking at that, don't worry, I'll tell you this one. This one I don't need participation just yet. It would be the x's, and the reason is that you have a single x here, and then you have a 2 there, so that means you have to alter something. Whereas if you look at the y's, you have a number in front of both, but not the same. So it's a little tougher. It's trickier, if you will. Not super tricky, but just enough. So what do you do? In situations like this, you want to ask yourself a simple question. And again, if you already know this because your prior experience in algebra, awesome, cool, no problem. But for those that have not seen in a while or they feel like they haven't seen in a while, the question you want to ask yourself is, what do I multiply? Once you establish which variable you're going to cancel, in this case, it's going to be the x's. What do I multiply by the first row? And by row, I mean equation, of course, to cancel x. Put x in quotation marks here. Cool. And in this case, you multiply by, use a different color here, a negative 2. How come? You need the negative so it can cancel out with the positive 2x on the second one. And you need it to be 2 so they can be the same number. So I apologize, my finger slipped. that means that this -2, it distributes to each piece of the equation. So I'll draw it down here as well. You have the same exact two sets of equations. I'll write down the second one because that's unchanged. 2x plus 5y equals -2. But now the rewritten first equation with this light pink or hot pink, you get -2x minus 8y equals -4. And now it looks exactly the same, if not super similar, with our first example set up, ready to eliminate, aka to add. So you draw your big line to represent equals and your big plus sign, and you do the same thing, right? These two cancel, so you're left with 0. These two combine to have -3y, and then -4 and -2 combine equal sign to have -6. And then if you haven't figured it out already, you're dividing by a -3 on both sides, and y is equal to 2 in this case, but we have to find x. So as someone mentioned, I forgot whose voice that was, and I apologize. Pretty sure I didn't recognize it. You go, hey, this is only half my answer. How do I get my other one? And as it was stated, you have to plug in +2 for y into either of the two equations to get your answer. So why don't you do that right now very quickly?
I'm sorry, can you just repeat that one more time?
Which part?
So I just need to hear it from after we solve for y.
Mm-hmm.
Hearing you say, solving for x now.
Yeah. Now that you have y equals 2 right here, you can use a different color. You take this number, and to get our other half of the answer, we plug it in to y here. But it could be either y. It could be this y or this y for the first or second equation, the original equations, and then solve for x. Is that clear now? Or at least more succinct?
Yeah, so when you're setting up your problem now, it should be 4 and in parentheses 2 or +2, and then you would just multiply.
Yeah, if you're using the first equation, that sounds like the first equation. So I pull the first equation over here, and you're left with x plus 4. Here is the light blue 2 equals 2, and then you solve for x, right? Before you can move the 4 times 2 to the other side of the equal sign, has to multiply by 8 to equal 8. So you subtract 8 on both sides. X should be equal to -6. So in this case, x is equal to -6, or you have the point -6, 2. I want to be visually recognizing both versions. Okay. What questions there, if any? All right, good. What we can do next now is we can continue onward and show you another variation where you have to manipulate again. Okay. So example 3 this time. Actually, before I get to that, I have a follow-up question. So this is just something that you can keep in mind. Let me write it out. My question is this. I said it in the last class, but maybe I need to write it out so for those that visually are watching, they can actually see it written out. So my follow-up question is, given example 1 and example 2 had solutions. Solutions or answers, however you want to think of it, involving a single point right? So that's what we found out. We found out that example 1, example 2, the solutions were a single point, -6, 2, and 1, 2. My question is, what can you tell me about pairs of equations respectively right? And your hint here is think visual graphs, right? In other words, if you don't know what I'm asking about in this case, right? Just imagine if you were to graph them. You don't have to graph it. I'm saying without graphing, if you were to graph example 1, these two equations, and then you know the answer or solution is 1, 2. Or example 2, you graph those two equations, and then you notice that the solution is -6, 2. What can you tell me about those two lines together?
They intersect.
They intersect, right? They intersect at a single point, so they will, let me write this out, they intersect. Right? What does that mean for us? It means that both sets graphs cross at a single point. Cross at a single point. That means that when you draw them, it probably looks something like this. Right? They intersect in some shape or form. And the unique aspect is the angle they create. You don't know what it is. Angle created from intersection. And I bring that up because I want to go over some of the other answers very quickly that my other class asked, or answered, I should say. So they said, what about parallel, though? What about parallel? Well, that is false because, sorry, I have to get the door.
Hey, quick question, sir. I'm gonna be with the neighbor across the street. We're actually looking for someone to. Our husband was painting himself,
Yeah.
but he said he doesn't want to do it. So I'm scheduled to come by to give him an estimate on his painting. I'm curious. Roof looks good. Your double pane windows, your landscaping, your inside, your doors. I mean, it's all pretty. Even your driveway looks good. It seems like you did quite a bit of work. I don't know if the next 2 to 3 years, like some of the painting.
Sorry, do you want to talk to my dad about this? Yeah. Okay. Hold on. Sorry, advertising, door-to-door advertising here. Hold on. I don't see him. Oh yeah, there's someone at the front door that wants to advertise if you want. If not, you can just tell them whatever. So anyhow, sorry for the interruption. So what about parallel, right? The thing though is that parallel lines don't do what? They don't ever cross, right? And the old name, the classic version of that is that they always talk about train tracks, right? So whether you're in the whether you are, hold on, why isn't my pencil connected? There it is. Whether you're talking about the MTA or the Metro North or Long Island Railroad, everyone always has the sense of, train tracks, right? They never cross. So when a student asks, oh, well, is the answer or is the solution parallel? Well, see, this is impossible because the equations share point. Both equations, right? From example 1 and example 2, share a single point. So the moment they share something, they can't be parallel. They have to be crossing one another, right? So that's something to keep in mind. The other thing that a student answered is that they said, what about perpendicular? Remember, we talked about that briefly in the chapter 4. So that was maybe about 2 to 2.5 weeks ago. What about perpendicular? Perpendicular, right? And remember, that looks like when graphs do this. You have a cross like this, and they cross like this. And if you recall, you got a little right angle. So this looks like our coordinate plane, right? The XY graph. But if you rotate it any way, it's the same thing, right? If you go like this, see, as long as it makes a 90-degree angle, that means they're perpendicular. So in this case, they do cross, but they cross uniquely, and it's based on the slopes, if you remember that from our lesson. So here I'm just going to write really quickly. Yes, the solution could be perpendicular. I'm not sure if you all remember, but to find whether it is perpendicular or perpendicularity, perpendicular, oops, perpendicular. The solution could be perpendicular, but the slopes must be, remember this term, negative reciprocals. Negative reciprocals. Reciprocals. That means that if you were to imagine this, right, you would say that the world of intersection, so visually, the world of intersection, I misspelled that. Intersection, right, is like this. You got a big world, and it's like this. right? And then what happens is that perpendicularity or perpendicular is within an intersection, but it's a unique aspect of intersection. So it's kind of like saying perpendicular. It's contained within intersections. Because if you're perpendicular, you're definitely an intersection, which also means that the world of parallelism, it never crosses with this because it's just out here. So you can see they never truly cross with one another. Right? They're not supposed to cross, right? If you're parallel only. If you're an intersection, you're an intersection only. There's no like, oh, we're parallel sometimes and we're intersections sometimes. And then the perpendicularity or perpendicular in this case is a form of an intersection, right? It's a unique aspect of it. So it's kind of like, oh, okay. I think I got it now. All right. So just wanted to point that out really quick because it's important. And I posed that question as well in my last class. Okay. But now I can move on to example 3. And then if you need to rehash this, you can ask me at the end of the lecture or rewatch the video once it goes live. 3, this one is unique because when I write out both equations, you're going to find out that there's no obvious answer or obvious variable to cancel. As you see, you have a pair of x's with both different numbers on top, 4 and 3, or in front, I'm sorry, the coefficients. And then you have the y's, and then you have different, again, coefficients leading the y's as well, -3 and a +5. So in this case, you actually have to manipulate not one, but 2 variables. And it really doesn't matter which one you do. It's just your personal preference at that point, right? So with that being said, I mean, it's not too much. I'm going to show you either way. What does anyone have a preference of which variable they want to see? I can tell you what happens in the book. In the textbook, they do the x's. And the reason they probably do that is that they work with smaller numbers, 4 and 3, 3 and 4. If I were doing this problem on my own, I can already tell you I would do the y's. And the reason is that I have a negative and a positive version of the y. Therefore, I have less room for error if I multiply by an incorrect number because I only have to multiply by positive numbers, not negative numbers. So that's my reasoning for it, but it's not necessarily the reason to end all, to say all. Okay. Anyone have a preference of which variable they want to see? Or they would like to see a particular variable, or
Can we do the y?
yeah, we can do the y. All right. So what do you have to multiply by? It's kind of like the least common multiple, right? Almost equivalent to the lowest common denominator. So what do you have to multiply 3 and 5 by so that they are equivalent to a number that they can cancel? Well, it's 15 if people didn't realize. So let me do both. So I have to multiply the top row, aka the top equation, by 5. And then I have to multiply the bottom equation by 3. Okay. And I'm going to rewrite both of these. I'm going to scroll down here so that people can see this in their respective colors. So in purple here, I have 5 times 4x, which is a 20x. 5 times 3y, -3y, which is minus 15y. That is not a y. And then 5 times 10, which is just 50. Same thing in navy. We have a 3 times 3, which is a 9x. 3 times positive 5y, which is a positive 15y. And then 7 times negative 3, which is negative 21. So now, not only do you have both your equations set up, they're set up in such a way where you can put your equal sign as a line. You're going to add them together or combine them, addition method, right? Then you cancel. Here you have, I'll do this in light blue. So you have 29x now. These cancel, so plus 0 essentially, but you don't have to write that. And then 50 minus 21, not 3, but 29, I believe. Make sure I did that right. Minus 21. Yeah, 29. That's good. And then as you can see, 29x equals 29. Well, this implies x is equal to 1, right? And you're going to take this x equals 1, you're going to plug it back into one of the two equations. Me personally, I would plug it into, I'd plug this x equals 1 to this one right here. Right, and let me rewrite that equation so everyone can see. So you have 3 times 1, right? X equals 1 plus 5y equals negative 7. So you do the math. So this becomes minus 3. You're left with 5y equals a negative 10. Divide both sides by 5. And then you're left with y equals negative 2. Again, or the point, what is that? 1 comma negative 2. So either of those answers are correct. Sorry, my wrist keeps on tapping the page. So there's that. There's that. One comma 2. Okay, negative 2. Okay. Therefore, you've seen the 3 varieties of from easiest to more involved, where you have an elimination method where you can cancel out a variable immediately, where you can cancel out one equation by multiplying by only 1, or in a case where you actually have to multiply by 2, right? In this case, the 5 and the 3. Now, if you remember from last lecture, we talked about substitution. We said, hey, what happens when all the variables cancel out? Okay. And I have 2 examples to show you of that really quickly, because since we did it already, you're familiar, or you should be familiar with it. In fact, your homework has some of it as well. Okay, here's example 4. Yeah, let me start a new page, it'll be easier. Here's example 4. And what if you have 5x minus 3y equals 15, and then y equals negative 5 plus 5/3 x. You can already see that the format or the layout is not like or not similar to what I introduced at the beginning. And you have to change that. You have to compensate for that, because that's what's going to make elimination method easy for you. It's supposed to be easy, right? And the more complicated the version or your setup, your layout, whatever you would like to call it is, the harder it makes the problem. So in this case, we have to, I'll put a little note here, note, we must fix the layout. In this case, we just subtract 5/3 x on both sides. And then we rewrite the equation. Now you have, I'll put it in order, don't worry. Negative 5/3 x plus y equals negative 5. And the original on top is 5x minus 3y equals 15. And you ask yourself, hey, which of the two variables is easiest to cancel? And hopefully what you've been seeing from the last 3 examples, that you notice that the y is easier. Not only is the y easier, it doesn't have any fractions, whereas x does. So the first row or first equation is fine. I'm going to multiply the second row by a positive 3, and then I'm going to rewrite this. So now, one last time, first row stays unchanged, 5x minus 3y equals 15. And now, this last row, what happens when you take 3, or 3 over 1 technically, times negative 5/3, or a third, the 3's cancel. So you're actually left with negative 5x. And when you multiply this way, you're left with a positive 3y. And then this way, you're left with a equals negative 15. So now we're set up in a way where you can cancel. But what happens when we cancel in this particular problem, right? There's your plus sign. I'm sorry, equal sign. And now plus sign. Remember, the line is representative of equal sign. And you see that these cancel. Start off with 0. And then these cancel. Plus another 0. Equals, and then these cancel. 0. So what the hell just happened here? We just had a 0 equals 0 moment. And remember, what we're supposed to do here is we're supposed to question it. And if you pull out last week's lecture from Monday, remember when we did it with substitution, I asked the same exact question. I'm not going to write it down again, but we ask ourselves, is this a true or false statement? So I'll write it up here, entire statement, but true or false statement. And then you ask yourself, is it true that 0 is 0? And then this implies, yes, it's a true statement. And when it's true, this implies as well that these two equations that you have seen right here, these original two, they are the same line. Both equations QUA equations are the same. What are some properties? Well, some properties are that they intersect, at infinitely many points. Remember, because since they're infinite, oh, I misspelled infinite. Forgot that N in infinite. Infinite. Since they're the same line, it doesn't matter which point you plug in. What will happen is that you'll always get no matter which x you plug in, you get a y, and then when you use the second equation, you get the same exact result as well. So they're intersect at infinitely many points. I already told you they are the same line. So again, same line, same exact line. And to a lesser extent, I'm putting in quotation marks, they're parallel, right? Well, of course they're parallel because they're the same exact line. So it's parallel to itself, if you will. But again, that's loosely. That's why I put it in quotation marks. So remember, whenever you have a substitution, a elimination / addition method, and you boil it down, you do all the math correctly, and you end up getting numbers, and the number statement is true, right? A number equals the same exact self, right? You find out that they're in fact the same exact line. And you can actually do that too. You could actually, here, this equation was almost the same exact setup. If you put in y equals slope-intercept form, right? Y equals 5/3 x minus 5. If you go to the second one right here, I guess I should do that in a different column.
Would you be able to scroll down a little bit so that way I can see the rest of the screen?
Sure. This one was -3y equals -5x plus 15. And then when you divide by the -3, lo and behold, you get the same exact answer, right? Y equals positive 5/3 x minus 5. So you can see they're the same exact thing here. And that's not by mistake, right? That was intentional. So there's that. That's another way you can determine that they're the same line without having to do substitution or elimination. And just let me know when you're done copying this, please.
Okay, I'm done.
All right, cool. Before I move on, what questions do people have about any of these or this concept? Because remember, this isn't a new concept. You've seen this before. It's just that you want to make sure that you understand it. Is this question going to be a lot or a ton on the final? I highly doubt it. Yet it's going to be extremely useful when you face any other math class after this, especially if you're FBM, AMC, ITM, entrepreneurship. When you go into statistics, you're not graphing too much, but you do definitely see them in what's something called linear regression. So it's linear, that means you have to work with lines again. And yeah, okay. What we're going to check now is what happens when you get the answer not equal to each other. So here's example 6. What happens when all the variables cancel out and you get a different result? What does that mean graphically? What does that mean mathematically? So I want everyone to try this on their own because this is the 6th example you're seeing. You don't need to hear me say it so much. And this time I'm going to give you a longer time, of course, not like the last one where I said, hey, someone, what did you get when you plugged in X for 5 or something like that? So let me make sure I get the charger out so things don't die. So with this problem, please do it on your own. Same method, right? And then what time is it right now? It's 12. So I'll give you 10 minutes. I'll give you to 22. We'll discuss it. And then this will be nice because this will be the end of the elimination method. And then we can talk briefly about inequalities and what happens when you have 2 sets of equations. So go ahead and do that right now, please. So it's 12 right now. Excuse me. Well, it's almost 13. So I'll give you to 23 then. You're done teaching. Internet wasn't working at hotel, so I'm using it here right now. In my room. So it's almost 23, but I'm not going to ask for volunteers this time. But what I will do is I'll start writing it out so people can take a look at their problems so they can see what's going on. And then if you're wrapping up or you're still working on it, this is good too, because you can see what you may have gone astray or could have done differently. This is what you should have gotten is in terms of the final result, that is, right? If you multiply by a different number, if you use the first row instead, if you multiply, divided, or well, actually you don't want to divide, but it's mostly multiplication. But you can think of it as division if you multiply by a fraction, say you multiply by a third or something like that. That's what you could have done. You could have reduced the first row by a third or a half or something like that. Okay, but the ultimate end is that you should have arrived at 0 equals -5. And you ask yourself, is that a true or false statement? And hopefully people realize that that's a false statement, right? This is false. Actually, you know what? Let me write it over here. There we go. 0 equals -5. Is that true? And the answer is no. This is a false statement. This implies that the equations have no points in common. They have no points in common. Remember, that means that they are parallel. And another way to think of it is that it has, the answer is they're false and that there's no solution, even though there is a solution, but you would hear it as no solution. Right? No solution meaning that no matter what points you pick in the world, you'll find out that no matter what you pick for X, it won't work for, what do you call it? It won't work for, there will be no point that will exist such that both of them are able to intersect, right? That there's no point for X or Y that you plug in for both equations that they'll give you an intersection. So that's what that means. Okay. What questions do we have on the elimination method, if any?
I have a question. How did we get 3 again? I know we had to, I believe it was like we had to use the least common multiple method in order
Yeah.
to get 3.
The reason it's 3 is that I, in my case, wanted to cancel out the x's. So 6's, or -6 in this case, is bigger than 2. What do I need to multiply 2 by to get to 6? And the answer is a +3.
Got it. So when I'm looking for the least common multiple, when I decide which row to use, I always have to refer to the opposite row to find the least common multiple, because that's where we're getting the 6x, the negative. That's where we got the 3 from, because we're doing negative 6x.
Correct. Yeah. It's just whatever is the biggest number in general. So if I didn't do the negative 6x, I would have done, say you picked 15y, for example. So when you look at the negative 5y, you ask yourself, what do I need to multiply negative 5y to get the opposite of 15y? Well, you need to multiply by 3, because then you get 3 times negative 5y, you get negative 15y. Is that a
Right.
little bit clearer now?
I did get 3, but what I did was I then did the top row as well, and I had got 1. So I
I
didn't
see.
step that I was
So
do.
yeah, you only have to manipulate. So this particular example, sometimes you have to manipulate 2 rows. The thing though is that once you manipulate 1 row and it gets you the results you need, as you saw right here when I drew the pink arrow going down to this set right here, since it already has what I needed to have, then you're okay, then you're good to go. Is that a little bit clearer?
Um, a little bit, yeah. I'm just wondering again. I know we went over this, but when would we have to manipulate both rows?
It's when you multiply both numbers, and what happens is that if you what happens is that if you how should I say this? If you What's the best way to say this? If you multiply 1 row and it doesn't give you the numbers that you want for the other row, then you have to multiply both of them. So if we look at number 3, for example, right? 3 and 4, these 2 numbers right here, they share something in common, but it's not one or the other. It's a number that they have to multiply to, which is 12. Same with here, 3 and 5. Whereas the first example, see 4 and 5, they share a common together, they have to multiply, which is 20. But this first one right here, right, that I wrote in light blue, it's 2 and 1. So what number do they share in common? If you multiply by the 1, it's just 2. Same with example number 4 here, right? You can see that we have these 2 numbers, 5 and 5/3. That's a little bit crazy, right? But then if you look at these 2 numbers, 3 and 1, the invisible 1 that's here, what number do you need to multiply so that they match? That's just a 3 in this case. So you can tell because, in this case, example 6, you can tell because looking at both the numbers and you're just seeing, do they share a common multiple? And what is that number? And if you can multiply one of the equations by a number to get it to that shared multiple, then you don't have to multiply by both. But if the number that they both share in common isn't either of the numbers, then you have to multiply by a number on both equations. How about that? Is that clear?
It's becoming more clear. I think I just need to see examples of both scenarios.
Okay. Well, the good thing is that you do actually have it. You have one double and then you have one single. But I'll assign it for homework if anything.
Right, I'll just look over again the lecture, just replay it so I can see it. So thank you.
Right. All right. What other questions? All right, so here we go. You've seen everything now with graphing, substitution, and elimination. And what happens is that the last section is having to do with inequalities. Yes, there's a section that has to do with applications of it. That's pretty much just word problems with the systems of equations, and I can show that in terms of examples. But I definitely want to show you something that is different in terms of, oh, if I see this, I'll recognize it, and then you'll know where to move from there. And that's the inequalities with the system. So let me show this to you. Nope, that's not the right section. The next one is, here we go. So this is section, this is in the algebra textbook, remember? We are in and there's a lot of varieties of these types of answers too. So there you go. So we're still in the algebra textbook, but I want to get your feet wet. Excuse me. And you'll be able to see what's going on. Page 648. Section 5.6. So here they'll give you an example like this. And they're actually to solve by graphing. And the unique aspect is that you have two of them now. Y greater than 2x minus 1, y less than x plus 1. And what I would do is that I would write from the beginning, just remember to go, oh, determine whether you're having solid or dotted lines to begin with, because we have the inequalities you can see right there. And just in case if anyone was curious, you'll never get an equation, at least as far as I can remember, where you'll have one inequality and one equality. Or if you do, it's very rare. As far as this textbook is concerned, though, you won't have a mix of things like that. So what I would do is with purple, I see this immediately, and then I got to remember solid line. And then in green here, I see this immediately, and I got to remember dotted line. Oops, that is not how you spell dotted. So let's graph this. Let's see what happens. Same stylization, but now we have to shade. So let's just graph first and see what happens. That's y. This is x. 2, 3, 4, 3, 4. So starting with, let's start with the first one, purple right here, right? We know the y-intercept is -1, so you start at -1. And the slope is not only 2, but 2 over 1. So that means we do what? From here we rise how many?
We rise 2.
Correct? And then we go 1 direction.
To the right because it's a positive? Or
Yep, exactly. No, that's exactly right. So that's great. So I'm going to draw my little arrow there. So let me draw this line. Again, this is a solid line, right? Whoa, what just happened? Why did I get a weird... break in my line? Okay, so here is my solid line, but then remember we have to test which way to graph. And it sounds like most students were okay with graphing with plugging in a point, right? So your test point is 0, 0, and then you test it out, right? You plug in your purple 0, and then you check, is that greater than or equal to 2 times 0 minus 1? And remember, you always pick a point that's not on the graph. So in this case, 0, 0 is the origin, and it's not part of this graph, as you can see. So is it true that 0 is greater than -1? The answer is yes, it is true. So you shade the region where the origin is. So you shade this side. But you have to do the same exact thing for the green as well. So let me actually shade this a lot nicer with lines so you can see what's going to happen. So So this entire region is shaded, right? Above the graph. That's one way to think of it as well. But when you look at this line, so you know that we're going to start at +1 this time. So this is in green now. And then our slope, it's 1/1. So same thing, rise 1, move to the right 1. So now you're going to get something like this. And then where does this graph lie? Well, I already know you're going to shade below it, but again, not everyone may know that visually. So your test point, again, is 0, 0, because again, 0 is not a part of the dotted line, and you test it. So you got 0 is less than 0 plus 1, and you check. Is it true that 0 is less than 1? And the answer is it is true. So where is 0, 0 compared to the green graph now? Well, now it's below the graph, so you shade down this way. Now, you personally don't have to do much. You just have to recognize how the graphs look. But this is important because this, if you were giving me a written exam, would be the solution, you'd be done. But the actual solution is where they intersect. So it's a little hard to see, but I'm going to still scribble it in orange. The solution is this portion right here. See, this is where they cross. And not only is this the solution is necessary to have the dotted green lines, as you can see right here. As well as that solid purple line. So that's the actual answer. It's that orange region right there. And I'll leave this alone, but just so you can see it on the video, what you'll see on multiple choice exams mostly is that they'll get rid of the lines like this and like this, and they'll say, hey, which of these answers is correct? And you're supposed to know that it's this shaded region, because then you know it's an easy multiple choice setup, right? I can shade this region, the region to the right, the region to the left, or the region right across from it. which are all possible answers, but only one of them is the valid answer. So this is what it normally looks like on a multiple choice exam. But you get this answer, and I'll put the lines back now, by understanding this right there in terms of where they intersect, all right? Now, obviously, we're going to do like a couple more examples of these, but before I move on, what questions do we have here on this? And I also want to show you what it looks like when you have different types of answers as well. Like what happens when you have perpendicular lines? What happens when you see this is an intersection? What happens when you have parallel lines? What happens when you have this type of line, you know? So that's that. All right, let's do another one like this. So single intersection and also when the overlapping graphic is happening, okay? So let's do another one like this. This was y 2x minus 1, x plus 1. Okay, we just did that problem. Now let's do this problem. Yeah, here we go. Here's example 8. So you're going to graph again. Let's say you had something like this. You had y is less than negative 1/2 x plus 3, and then y is less than 3x minus 4. So I'll walk you through this one again. It's already set up in slope-intercept form, which is very nice. So you got your y, you have your x. So I'm going to go 1, 2, 3, 4, 5. 1, 2, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. And I'm going to do the first one in purple. So we start at positive 3. And since the slope is m equals negative 1/2, right? We rise 1, but this time we run to the left 2 because why again?
Negative. It's a negative number.
Negative in the slope, right?
Negative in the slope, yes.
And then, yes, negative number. That's what you meant. That's fine. And remember, I didn't say it immediately from the beginning, but remember, this is a dotted line as well, okay? So this is dotted here. Dotted. So now I got my 2 points, and let me draw my little dotted line. Oops, that's not dotted. Let's try that again. Okay, there's your dotted line, and you still have to test the point, right? So in this case, we're going to test 0, 0, because you can see the origin is not a part of this line. So you're going to test, and then remember, for some people that are saying, well, why are you choosing 0, 0? Well, first of all, it's the easiest. That's 1. But 2, you could choose any point you want. It's just that 0, 0 is the easiest. And you remember, you pick a point that's not a part of this line, okay? Or in this case, this inequality. So you have, I'm looking at the original equation, you got 0 for y is less than negative 1/2 x, which is 0 as well, plus 3. And then you check, is it true that 0 is less than 3? Question mark. And the answer is yes. So when you graph, you're going to graph the region where the 0, 0 test point was. So it's down this way. 1, 2. Okay, so that's it. For the other one in green, we have, again, dotted line. we have this -4 where the y-intercept is. So that starts at 1, 2, 3, 4 down here. And this slope, a lot steeper now, right? M equals not just 3, but 3 over 1. So rise 3, 1, 2, and 3, and then you're going to move to the right 1. Now, obviously, I know it's a little bit, what's the word I'm looking for? It's being covered, if you will, by the purple. But even if I erase this purple line right here, you can see what I'm doing, right? Start at -4. I went up 3. Oops. I went up 3, and then I went to the right 1 because it's a positive slope. And then you graph your line, dot it again, right? So dot, 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 dot. So there's that, and then you have to do another test point as well. This graph, as you can see, does not align or go through the origin again, so you can use 0, 0 again, and then now you just do the same exact thing for this one. You take the original equation, so you got y0 is less than 3 times 0 minus 4. So this is the second equation I'm doing now. So you check, is it true that 0 is less than -4? So this is a false. So then that means you got to shade opposite of the point 0, 0. So 0, 0 would normally be on the left side here. We're actually going to shade the right of it right now. So it would look like this. And then that means that the solution is where they intersect. So it's not above here in the green, it's not above here in the purple, but I'll scribble it for you. It's between these two dotted lines right here. Right? So it's the purple line going down, or inequality going down right here, as you saw. That's its border. And an arrow sign. And then you see the green or dark green here, that it's going down this way as well, dotted. So this question can be an easy multiple choice question as well to really fool students, because you can have the same exact picture like this, and then I can do both lines solid. I could do one solid, one dotted, one dotted, one solid, and both dotted. And it's the same exact picture. So you really have to know whether which equation is dotted or solid just by looking at it. Yeah, you can work out the entire graphing and everything, but there's a lot more work. So that's in a nutshell what it looks like. The only thing that you're physically missing is just seeing all possible kinds of graphs. Now, obviously, we don't have time to go over all of them, yet we will go over unique ones come Wednesday. Okay, so let me save this onto Blackboard so that you have this PDF immediately available to you. Section 304. And remember, on YouTube, you're going to have this video posted because my last class I had internet trouble, sadly, so their lecture was cut a little bit short, and they will rewatch your video because it has everything they'll have everything here. So that's with the whole